All right. Sorry about that confusion. Dongle did not seem to work, but I am JP Smith. I'm Japesinator on Twitter, or Japesinator on GitHub, or Japesinator on large swaths of the internet. You can go find it yourself. Here to talk about curry and tarts, or more weird math nerd stuff, because you probably didn't get enough of that with Parker. So, the big problem we're looking at today is that reasoning about programs is a really hard problem. Making guarantees about what programs will do is a semi-impossible problem. And what runs in your head when you're designing it, the code you write, the intentions you have, and even what happens in development can vary vastly from what happens in production. And taking into account these differences, planning for them, and making them not break things is largely what keeps all of us employed. So this bites us, like I said, in way too many ways to cover in a 20-minute talk. But for example, side channel attacks are a really good example of this, where we build these literally mathematically perfect crypto systems that we can't break the math on, we can't reverse the encryption in any way. So we just look at how long they take to run, the kind of power they consume, the CPU operations they use, and break them that way. Like, equality, for instance. You might want to say whether or not 2 bytes to 8-bit strings are equal. So we're going to do this in a really obvious way by just looping through every bit in the byte. If it's equal, keep going unless we're out of bits. And if it's not equal, then we stop. We say, these are not equal, and we fail. But this has weird side effects with time. Like if we're comparing 2 bytes that are only different at the end, then it'll compare the first, keep going, compare the second, keep going, compare the third, keep going, compare the fourth, keep going. Whereas if it is only different at the first, then it'll just stop there. So if I'm attacking this, if I have, say, a password checker that just says, is your password equal to the string entered, then I'll enter 2 passwords, one of which has a first bit of 0 and one of which has a first bit of 1. Whichever one takes longer has the correct first bit, because it ran more loops. So then I repeat that for the second bit, and I can crack the password in O of n time instead of O of something large, which is what it usually takes. It basically lets us binary search through whatever we're comparing for equality. Now, this happens in all kinds of things. Exponentiation, it happens really frequently. Multiplication, addition, basically everything you can do with numbers. If you do it naively, then bigger numbers take longer, and numbers with more ones take longer because we have to do more work. So in 1999, Coker broke RSA doing this. In 2003, Bonet and Brumley broke SSL doing this. In 2005, Bonet broke AES doing this. Basically, any significant crypto system that's used in production has been broken multiple times by exploiting just timing attacks, because when we do the math, we look at how does this work on paper given infinity time and resources, and not how does this work on my actual server running using actual CPU cycles. Which makes sense, obviously. It's much harder to design for something that's going to run like that, and to guarantee that every way this runs, it takes the same amount of time. And even if you think you're right, then compilers optimize, weird code paths get taken. It's a really hard problem. So we can have lots of things to prevent this. Bad software, unpredictable software, software with bugs in it, has been around for about as long as software has, and we've come up with a bunch of strategies. So code review is awesome. Unit tests are great. We can do property-based testing or fuzzing, where we generate 1 million unit tests automatically based on the right shape of things, but all of those only go so far. All of those only say that this function will behave as we intend in these cases. So we cover some set of everything that could happen and say, okay, these cases are probably typical of everything. There won't be any weird degenerative inputs, any odd code paths generated by malicious hackers that cause this thing to break or behave unexpectedly. And that assumption has a pretty poor track record, all in all. Betting that things will work as we've tested them basically never works for anyone. So it would be really nice if instead of saying, for these cases this works, we could say, for all cases, for any possible case, here is a proof that this works. And then to totally switch topics for a minute, we're going to talk about a way to do this. Most people who have developed have seen type systems, basically. Ways of putting variables into different categories, into different types, into different sets. So like we can say that 5 is an integer. We can say that we can even type functions. So we can have some function f that is a function from integers to strings. Like maybe it just prints out the name of the integer. So it goes from 5 to FIVE. And if we have that type of f, and then write f of x equals x plus 3, then my compiler will bitch at me because f of x plus 3 returns an integer and not a string. So it's nice to have the computer to lean on. And actually, types end up being something way more significant once you pull a little higher mathematics into it. That is, types end up being basically the same thing as propositions, and writing functions or objects or whatever with those types, filling those types, is a proof of that proposition. And then our compiler actually checks these proofs when it checks something like f of x has type of an integer to a string. And so we can essentially formally verify some properties like f has type of an integer to a string. So if we have a function like length, which just returns how many characters are in a given string, then that's also a proof that if there exist strings, there exist integers, because it gives us a way to turn strings into integers. And any function that has that type is a proof of that proposition, and when it compiles, we have verified that that proof holds. Now, with really fancy, dependently typed languages, we can actually have functions to types from anything else, which lets us write any proposition we want as a type. So instead of writing like something trivial, something kind of useless, like if there exist strings, there exist integers, we can write something like the Pythagorean theorem as a type, and then a function that fulfills that proves the Pythagorean theorem. And more importantly, we can write about our code. We can say that our code will have this property in a type, and then when we compile our code, we have proved that that property will always hold. So there are languages right now like Idris, Agda, Coq, where you can write any logical proposition in this type language and then formally verify it, just like compiling regular code, just like checking our function f earlier goes from an integer to a string. And then this really makes a language the same thing as a proving assistant, and we can pass around these proofs, these propositions, just like integers or any other kind of object in the language. So we can make functions that, for instance, ask for a proof that their inputs follow some property or are correct. We can make a function that takes the first element of a list and requires a proof that the list is not empty, so it never fails or returns null pointer exception or whatever. But we can also do this for crypto. We can look at crypto functions. We can look at, say, our equality function earlier and say that this will run in constant time and encode that as a type. So just as certainly as we prove that the existence of integers implies the existence of strings, we can prove that our implementation of equality always goes in constant time. So, for example, we can start with a really simple function that just goes from 2 bytes to a bit. 1 if they're equal, 0 if they're not equal. Then we can add a little bit of trickery to add a basically timing counter to that. So it'll return both a bit for the result right here and a natural number of how many operations took place. So 0 operations, 1 operations, 2, 3, 4, whatever. Any integer greater than or equal to 0. And then here's the implementation. We're going to gloss over that because this is a 20-minute talk. And then finally, we can prove this. So we can say that for any A, B, C, and D, which are bytes, then the time that it takes to compare them, the time that it takes to compare the first two, is equal to the time that it takes to compare the second two. Or in other words, our function cannot be timing attacked because any pair of bytes takes the same time to compare as any other pair of bytes. So we can't do that binary search like we did earlier to suss out passwords or confidential data or whatever. And we formally prove that. We haven't just tested, here's a bunch of cases where we tried it and it took the same time. We have shown that for all cases, for any case you can imagine or implement in this language, this bad thing won't happen. And I have working code doing this whole thing at this goo.gl URL right here. If you want to see it, if you want to play with it, it actually runs and you can do real comparisons and see how long they took, see if the proofs work, which is cool. So, oh, barcode. You might want that. Wait, not quite done. All right. All good? All good? Cool. So, disclaimers are, right now, this mostly works way up in the ivory tower of people who stare at weird PDFs about math all day. This is still quite a few steps away from mainstream production. And please do not take these weird academic languages and try to write code for your job in them, because then really bad things happen, plague of locusts over the land, I don't know. Not good. Things break. Write fun code in them, see what you can do, try out whether or not this can work, but very, very not production ready, not even version 1.0, etc., etc. Also, the important part of this talk is not necessarily we can do equality in constant time. It is we can prove these really hard to reason about properties, and we can formally show that for this important code, there is no possible way to break it, rather than just, we tried really hard to break it for a long time and couldn't. Which is an interesting new approach to security, where instead of just trying to break it over and over again, we show that it is totally impossible to break under any circumstances and actually have a chance of that being correct. Any questions in the few minutes I have left? 3 minutes. Any questions? All right. Thank you.